In this video, we are going to practice drawing resonance structures, ranking them, and drawing curved arrows. If you haven't seen my video showing how to do all of this, then go ahead and watch that, and then come on back and let's practice. For this first problem, the first thing we're going to do is decide which of these structures is not possible. Okay, so firstly, we don't even know which one is the original or anything like that. So we need to make sure that all of these have the same connectivity. So we're going to start at the bottom here, H3C. All of those have that, followed by a nitrogen, followed by oxygen, okay, and then at the top, H2C. Okay, all of them have the same connectivity. It's a good start. Next, we're going to make sure that none of them have more than 8 electrons attached to each atom. So we're good here. This carbon has 4 connected to it. This one has 3, okay? We have 8 electrons here, 8. Keep going. 4 connecting to the nitrogen. Our oxygen's happy. Good, good. We get to this one and oh, we see this nitrogen. It's got 5 bonds connected to it, which means it has 10 electrons. This cannot be. It is a second period element, and so it can only have 8 electrons. We won't talk about ones above second period at the moment, but for now, let's just talk about second period. They only can have 8 bonds maximum. So let's look at this next one. We're good to go. All right, so we know for sure that this C is the one that cannot possibly be a resonance contributor. Next, we're going to draw curved arrows to show how the electrons move to the next structure. Now, if I'm comparing A and B, I need to see what's different. For this one, the nitrogen has a lone pair. For this one, it has a double bond. Now, this positive is here, and then it's up here for this one. That means that for this one, there must be an arrow going from nitrogen up to carbon, because we know that on the back end of an arrow is where it's going to become more positive, and at the pointy part of the arrow is where it's going to become more negative. So what we're going to do is we're going to take this lone pair and point it onto the single bond to create this double bond, okay? Next, we're going to compare B and D. Again, we see the difference is we have a negative on this oxygen and a negative up on this carbon. The oxygen down here is single bonded, double bonded here. So something we can do, again, we have a lone pair up here on the carbon, so something must have come up to give it that lone pair. So we will draw these lone pairs to create the double bond between it and nitrogen. And then we have a problem with this nitrogen. It's got 5 bonds, just like we see here in the C. It would have a double bond here, a double bond here, and a single bond here. So this double bond must have to come up onto the carbon, and we see that it does here. Okay? So that is how we get from B to D. The next question asks us to rank the structures. So if we're going to compare A, B, and D, we need to know which one's the best, second, and worst. So the first rule is to make sure that every atom has its full octet. For the first question, we made sure that nothing had more than an octet. For this one, we need to make sure that it doesn't have less than an octet. So let's start with A. We see here with carbon that because it is positively charged, if you ever see a carbocation, carbon with a plus charge, that means it is missing one of its bonds. So it has 2 hydrogens and a bond to nitrogen. That's it. It only has 6 electrons. So this guy did not pass the octet test. Next one, we have our full octet here, full octet. Good, good. Everybody here is happy. Let's move on to this one. We have our full octet. It's not the best way to have an octet for a carbon, but that's fine. Let's move on to nitrogen. He's happy. Oxygen's happy. Carbon's happy. He passes. So we know that A is the worst. We'll give him a number 3. The next thing we are going to compare is formal charges. For B, we have 1, 2 formal charge, and for D, 1, 2 formal charge. So that's not going to help us any. The next thing that we can look to rank is where we find the negative. So for this one, negative is on the carbon, and for this one, the negative is on the oxygen. We want the negative to be on the most electronegative, so the oxygen is where we want it to be. So B would be our major contributing structure, D would be our second most contributing structure, and A would be our third contributing structure. For this next one, we are going to draw one other possible resonance structure and then rank the one that's already there and the one we've drawn. So for number 1 here, we have a positive and a negative charge. The best thing we can do is flow negative to positive. So let's see what we can do here. We have this lone pair of electrons and we have a carbocation. If we take that lone pair and point it down onto the single bond, it will create a double bond. If we are to compare these structures, the first rule says we want everybody to have their octet. This first one has a carbocation. He has not met his octet. The second one has all his octet. So this is our major contributing structure. If we look at this next one, number 2, we see we have a positive here. We see we have a single bond. That can't move. We have a lone pair, and we can't move it onto a triple bond. We can't go more than 3 bonds. But we can move part of this triple bond, either to the left or to the right. If we move it to the right, make it a lone pair on the nitrogen, we have to remember that the back end of the arrow will always make the atom over here more positive and the atom over here more negative at the pointy end. This nitrogen is already positive. We do not want to increase his positivity. If we point it the other way and make a double bond on this carbon-nitrogen, that is not possible because this carbon here is sp3 hybridized. It has 3 hydrogens already, and it has a bond to the nitrogen. It cannot have a double bond here. But we can move this onto the nitrogen to create a lone pair on this nitrogen. It would create the following structure. If we were to rank these two structures, first we start with the octet. If we look at this one up here, the carbon has its octet, nitrogen has its octet, this nitrogen has its octet, so this one is good. If we look at the next one, again the carbon is happy, this nitrogen is happy, 1, 2, 3 bonds, but this one, he has his 2 bonds and only 1 set of lone pairs. That means he only has 1, 2, 3, 4, 5, 6 electrons. He is not happy. He does not have his octet. So this first structure would be our most contributing structure. If we move on to number 3, we see that we have a carbocation again. We have an oxygen with lone pairs. The only possible thing that we can move here are lone pairs. We are going to move a lone pair towards the positive charge to increase the negativity of that carbon. The following structure would be drawn. In order to rank them, we will need to again check the octet. For this first one, we see that we have a carbocation. Right away we know it doesn't have its octet. For this next one, we look at the carbon. It has all 4 of its bonds. It's very happy. Oxygen has 3 bonds, which is unusual for it, but it has 2 lone pairs. That makes it happy. Has all 8 of its electrons. It is the most contributing structure. For these next 4, I have drawn them in their bond line form, which makes it a little bit more tricky. We have to remember where the hydrogens are on these carbons. For number 4, we see that we have a positive down here on this carbon and a negative up here on this carbon. The only things that we would be able to move are the lone pair and the double bond. Now, in general, we like to move things from negative to positive. So I'm going to move this down here. Now this may seem all right. We will end up having a double bond here and a double bond here. Carbon can take two double bonds. However, the hybridization on an atom can't change. And this carbon right here already has 4 connections. It has a bond to carbon, a bond to hydrogen, and 2 bonds to this carbon over here. If we make a double bond here, this carbon is in trouble. So what we need to do is move this double bond onto the next carbon. This will make this next carbon happy because he only has 2 hydrogens. We know that since he has a positive charge, he can only make 3 connections when he has that positive charge. So giving him a double bond will give him 4 connections, which will satisfy his octet. This carbon up here also only has 2 hydrogens, and a double bond for him will also make him complete. We can see from this that this structure up here, because he has his carbocation, he does not have a complete octet, whereas this structure is complete. He will be the major contributing structure. For number 5, we do not have any positive or negative charges. We have lone pairs and we have double bonds. As we move electrons, it will create negative and positive charges since it doesn't have any at the moment. Let's start with this double bond here. We will draw that double bond to give lone pair to the oxygen. It will create the following structure. You can see from this structure that we have created a carbocation. To help remedy that carbocation, a lone pair can be brought from the oxygen and create a double bond. If we are to rank the following structures, we will see again which ones have their octet. If we look at this first one, we see the oxygen has its octet, this one does as well, and so does the carbon. So we will give that a check mark. This next one, we have a carbocation. That means he does not have his octet. For this next one, oxygen has its octet. This oxygen, although he's not overly happy, he has 3 bonds and 1 lone pair. So he has his octet as well as this carbon in the middle. So we know which structure is the worst. Least contributing, we could say. Between these two, we will then consider the separation of charge. This one up here does not have any formal charge. That would make this one rank the best. This one down here has 2 formal charges. Therefore, this one is second best. For number 6, we see that we have a negative on the carbon and a positive on the nitrogen. We have 2 lone pairs we can move and a double bond. In general, we like to move from the negative to the positive. We will take this lone pair and draw an arrow onto the single bond to make a double bond. This nitrogen could move his lone pair towards the double bond to make a triple bond. However, this nitrogen cannot handle that many bonds. He already has 4 bonds. In that case, we could take one of the bonds here and put it on the nitrogen as a lone pair. However, he would still then have a double bond here and 2 hydrogens here, as well as a lone pair. That would be 10 electrons. That cannot work. This lone pair is going to need to stay where it's at. However, it's not happy, the nitrogen, as it is, it will have a double bond here and a double bond here and a lone pair. So it would have 10 electrons. So instead of moving this lone pair, what we need to move is this double bond onto the nitrogen without moving the lone pair first. It would make the following structure. As we see, this carbon that had 2 hydrogens before is happy with the double bond because this carbon will now have 4 bonds. This nitrogen has the 3 bonds and the 2 lone pairs that it likes to have, as well as this nitrogen here. 2 bonds to hydrogen and 1 to nitrogen and the lone pair. We see that he has his full octet. This structure up here, we have a carbon that's got his full octet, Nitrogen has his full octet, and this nitrogen also has a full octet. So comparing octets will not help us here. The next rule, however, compares formal charges. This top one up here has 2, and this bottom has none at all. So this structure is going to be our major contributing structure. If we move on to number 7, we see that we have a negative charge, but no positive charges. So we will just have to move this negative charge around to help balance the structure. We see that we have lone pairs, and we have a double bond. We can move away from the negative. We're not going to want to move this double bond towards the oxygen, as that would make this positive and this more negative. So we're going to want to move the negative away from the oxygen. We will draw from the lone pair onto this oxygen-carbon bond to make it a double bond. Now, this carbon here would then have 5 bonds. Double bond here, a double bond here, and a hydrogen. We will then need to move this double bond onto the carbon. It would create the following structure. If we were to compare these two structures, we see that the oxygen, the carbon, and the carbon have their full octet. In this structure, we see that this oxygen, this carbon, and this carbon all have their full octet. So the octet is not going to help us here. The next thing we can check is if they have different amounts of formal charges. However, they both have one negative formal charge, so that rule is not going to help us. The next rule is to determine if the negative is on the most electronegative atom. This one is on the carbon, and this one is on the oxygen. Oxygen is more electronegative, so this would be the major contributing structure. For this next problem, we see that we need to draw all possible resonance structures and rank them. For this molecule that we see here, we see that we have a positive charge, a double bond that can move, and a lone pair that can move. Those are the only things. In general, we would like to move things towards the positive charge to stabilize it. So we are going to move this double bond in the direction of the positive. But we are going to take it in baby steps. We are going to draw it onto the carbon. This will create the following structure. We see that we have made a second positive here, but we are going to slowly again move this structure around because we were trying to make all possible resonance structures. So we will take this lone pair, we will create a double bond here. This will stabilize this positive charge. Now that that is stabilized, we see that we still have one more to stabilize. So we will take this lone pair and we will draw it down here to make a double bond that will stabilize this carbocation. We can see with that arrow drawing the electrons down here, we have created the positive up here on our nitrogen. Now, this is fairly stable and we'll work more with this when we do the ranking, but there are still more resonance structures to be had. And this is where we consider what can we do to move these things around. If we were to try and draw these electrons coming over to this part of the structure over here, the problem with that would be that this carbon right here is sp3 hybridized. sp3 hybridization is the wall for resonance. That's where it has to stop. So these electrons can't move here. They could technically move onto your carbon here as a lone pair. However, arrows moving away from the nitrogen will make this increasingly positive. We don't really want to do that. So we could then draw this down here, but again, same problem with this positive. Let's just stick with this double bond here. He used to be over here on this lone pair, as we had him over here. So we're going to continue to move him to the right. We will move him onto this carbon here as a lone pair. Again, now we're going to leave this double bond alone. This lone pair here, can we continue to move him to the right? And the question lies with this carbon here. This carbon here is also sp3 hybridized, which means he cannot accept a double bond, and he can't change his hybridization during resonance. So the answer is no, it can't go that far. We are stuck only drawing our electrons going this far. And any electrons can only go, again, this far going this way because of that sp3 hybridization, and this one over here, it can't go off to the left. So this would be our last resonance structure. The next thing we're going to need to do is to rank these. Now, if we remember our rules that we've been practicing, the first one is looking at our octets. So let's start here. For this first one, we see we have a carbocation, therefore it does not have its octet. This one has 2, definitely does not have its octet. This one, again, a carbocation. Looking at this one, the positive is now on the nitrogen. The carbons are all happy. This has its full octet. Now let's look at this next one. Oh, look, again, we have a carbocation. So that one is not winning. Okay, so this is going to be our major contributing structure. Let's rank the next 4. The next rule compares how many formal charges each structure has. This first one has 1. This next one has 3. This one has 1. And this one has 3. Between this one and this one, we need to see which one is the winner. So we can compare with the next rule, and that is that negatives need to be on the most electronegative. There are no negatives, that's not going to help us. The last rule would be carbocations. They need to be the most substituted. So if we compare 1 and 3 here, you can see that this carbon is attached to a carbon here and a carbon here and a nitrogen. This carbon here is attached to a carbon here, and a hydrogen. We can conclude that 2 carbons and a nitrogen is better than 2 carbons and a hydrogen, so we will give this one the number 2 ranking and this one the number 3 ranking. Between the second and fifth structures, we see that this one has 2 carbocations and this one has 1. The importance of that is that our octet rule says that we want everybody to have their full octet. So going back to that very first rule, this one breaks the rule more than the fifth one does. So we will make this one to be number 4, and we will make this one to be the fifth and the last contributing structure. If you like this video, please subscribe, and in the comments, let me know what you would like to see in future videos to help you pass your chem classes.